Welcome, welcome, ladies and gentlemen, to a very exciting episode of Dave Does Math from Home. Today, we start Calc 3. It starts with this, right here. There is a lesson for today. We're going to end up talking about section 13.1. It's vectors in the plane. Before that, I want to give you a little bit of context about Calc 3, since this is the opener, the beginning of it all. Calc 3 is not actually the name of this course. Multivariable calculus is the name of this course. I'm going to call it Calc 3 a lot because that's just how I think of it. But the name is significant. It's not really going more in-depth into calculus ideas. We're not going to pick up where we left off in Calc 2 and like keep going to see how far that rabbit hole goes. We are going to sort of expand the ideas of calculus in a different direction. We're not going deeper, we're going wider, as it were. All of the calculus that we've done so far has been in two variables, x and y. And so we have these functions. They always end up looking like this. Y equals some function of x. And in these functions you have x as your independent variable. That can be anything you want it to be. On the x-axis, you get to choose whatever you want, and your function based on that will determine a height above or below the x-axis on the y-axis, and that, when you connect all the dots, you get some curve. Because every single one of these x values is going to give you a y value. So that's your dependent, where your y is your dependent, x is your independent relationship in 2 dimensions that gives you a curve. We want to be able to extend this beyond 2 dimensions. 2 dimensions is ultimately going to be pretty limiting. So one of the major things we're going to end up doing in the course is we're going to take a look at a different kind of function. We're going to see things that look like this. And I'll explain more about these later. But essentially this is z as a function of x and y. And so in this case, x and y are still on the xy plane. That hasn't changed. Now both of these are independent variables. Instead of choosing a single position on the x-axis to get a height on the y, we now get to choose any point we want on the entire plane. So if we choose this point right here, this is, I don't know, 2, 3. If we choose the point 2, 3, we can plug that point into this function and it'll give us a z value some distance above or below the plane. This is a 3rd dimension. It is coming out of the board into 3 space. And the height above or below this plane is determined by the function. And so when you do that to every point on the plane, you don't get a curve, you get a surface. So instead of like a parabola being a curve, we could have like a paraboloid, which is like a bowl-shaped thing. Or we could have some sort of 3-dimensional sinusoidal wave. Like we can model ripples across the surface of a pond using this as being the height of the wave as the dependent variable, and your position in the pond being your independent variables, 2 of them. So this is ultimately the goal that we want to get to. We're going to have a lot of fun with those, doing derivatives, doing integrals in 3 space using extra variables. And this is one of the ways we're going to do it. Another way we're going to do it is using vectors. We're going to end up doing a lot of calculus on vectors. Vectors are a really, really easy way for us to sort of extend some of these ideas into 3 space. So let's talk about what vectors are. What is a vector? I think the easiest way to describe a vector is as a magnitude and a direction. So it is it's like an arrow. Usually gets drawn as an arrow anyway. Lots of times vectors represent motion or movement or force or some sort of push. They get used a lot in physics. Hopefully you're at least vaguely familiar with vectors. They do get used in other things. And we kind of write them as if they were points sometimes. Hopefully the words magnitude and direction are sort of bringing you back to when we did pre-calculus and we were talking about polar coordinates. Polar coordinates were what took us from expressing this point up here. It's 3, 4 in rectangular coordinates because you got to go over 3 and up 4. But instead of expressing it as 3, 4 in polar coordinates, we talked about this distance and this direction. That distance is the magnitude. And sometimes, if you're talking about a motion vector, it will literally be a distance. If you're talking about a force vector, that's when things like magnitude become the better word to use than distance. Because with a force vector, it's not actually a distance you're traveling, it's a quantity of force that you're putting in that direction. So magnitude is sort of the catch-all term. Sometimes it means distance, sometimes it means size of the force involved. But in polar coordinates, it means a distance, and the direction here, I think this is something like 57 degrees. I could be wrong. So this idea of magnitude and direction feels a lot like polar coordinates, but we're going to mostly write vectors using rectangular coordinates. So right now this is a point. It is a position. It has no magnitude because it's just a point. It has no dimensions to it. It can't have a size. And it has no direction. It's not going anywhere. But we could talk about the vector that goes from 0, 0, the point, 2, 3, 4, the point. This vector, I'm going to write vectors usually with little hats on them, like arrow-shaped hats. So this is V with a little arrow-shaped hat on it. That means vectors. The book is going to alternate between writing vectors using this little arrow-shaped hat, and sometimes it'll just write vectors in bold. I can't write bold with my markers. I only have one size of marker, so you don't get bold. But this is the vector V that goes from 0, 0 to 3, 4. We're going to use triangular brackets, and we're just going to call it 3, 4. So now, if we want to talk about this as a position vector, it's going to give us the same position as this point 3, 4. But it's going to give us that position by expressing some sort of travel or distance from 0, 0 in this direction, with this as a starting point and this as an ending point. And on some level that kind of feels like a trivial difference. 3, 4 in parentheses means the point, and 3, 4 in triangular brackets means a vector. But it is going to be significant in a couple ways. First of all, now that this is a vector, we can sort of move it around. If I say that the vector is 3, 4, that means that it'll take us to the point 3, 4 if we start from 0, 0. But if we start from a different point, if we start from -2, 1, If you start from right here, this vector 3 comma 4, that'll take us to 1, 5. So it's the same vector, we can just move it around. We can do some other stuff to it too. We can multiply it by things. We could talk about we could talk about 2v. The good news about this kind of multiplication is that this multiplication works exactly like you would expect it to. 2v is 6 comma 8, still in triangular brackets. And if we start from 0, 0, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, it'll take you to the point 6 comma 8. This is 2v. That's not something that we can do with points. You can't multiply points by numbers and get a different point. That's not how points work. Points describe a position, and it doesn't make any mathematical sense to multiply a position by a number. But if you have this object that is some sort of distance and direction, you can multiply that thing by 2. You can multiply that thing by 2 or 3. You could multiply by negative 1. You can multiply by 1/2, make it smaller. Negative 1 will, let's look at what happens when you multiply by negative 1. Negative v is going to be negative 3 comma negative 4 in these triangular brackets. So that will take us down this way. There's negative v. So these offer us a lot more flexibility for working with them than just points do. And sometimes we're still going to want to use them sort of vaguely as if they represented points, because again, if we're talking about position vectors, you can talk about the point 3, 4 as a point 3, 4, or you can talk about it as the terminal point of the position vector v, which is 3 comma 4. So they have a lot of the same functionality as points do. We can talk about vectors as if they were positions or give you positions, but we can do a lot more with them. We can multiply them by numbers in a way that's pretty intuitive. We could also add them together if we come up with a different vector that we want to experiment with. The two standard issue vector names that get used the most are u and v, so let's come up with a u vector. I'm going to leave v as 3 comma 4. Let's come up with a u vector. I want u to be negative 1 comma 3. So as a position vector, this would take us back 1, down, no, back 1 and up 3. So that's u as a position vector. And we can do things like add these. We can talk about the vector u plus v and this is actually pretty powerful. You can't add points together, but you can add vectors together. So u plus v, fortunately we add these in a very intuitive way. You just add piecewise. So negative 1 plus 3 will give us 2. 3 plus 4 will give us 7. This is the vector u plus v. You can draw this. 1, 2, 6. Vector u plus v as a position vector will go from 0, 0 to the point 2, 7. This is u plus v. And here's what's really, really cool about drawing these. If we draw v, v was 3 comma 4. So here's v. If we start from the end of v and then draw u, u is back 1 and up 3. So back 1, up 3. Adding together the vectors u plus v end to end gives us the vector u plus v, which, when you say it out loud, sounds trivial and stupid, but it's very nice to know that this works graphically. And it's commutative. If you wanted to start with u and go back 1, up 3, and then add v to that, so we go over 3, 1, 2, 3, and up 4, 1, 2, 3, 4, you get a nice little parallelogram. So the vector addition plan works out really nicely. Multiplication works how you would expect it to. We can use them to describe points on a plane, or we can use them to describe motion from points on a plane. That's sort of the nice thing about V, is that once you use it to describe this motion on a plane, it's no longer fixed to being this point. You can move this anywhere you want. And you can attach it to the end of things, or attach things to the end of it, or you can double it, or halve it, or multiply it by numbers. I do need to say that when you multiply it by a number, 2v, this is called scalar multiplication. It's called scalar multiplication because it scales the vector. If you multiply something by 2, you get something that's twice as big. There's one more thing I need to say about vectors, and we'll talk about magnitudes in a minute, but first, here's Mojo. She's terrible. Bye, Mojo.